This video will cover all of the notes that go with section 10.2 in the gas laws chapter. So these are sort of the basic gas laws that we will ultimately get into more complicated ones. But these first few deal with just a few variables changing at a time, and then will lead to something called the combined gas law. So, section 10.2. The first thing we need to talk about before we get into the actual equations is we need to make sure that you understand what we mean when we refer to the term directly and indirectly, or we could use inversely. They're essentially the same thing. So, when you have a direct relationship, so again, that's just another way of saying the same thing. When you have a direct relationship, that means that both variables change in the same way. So as one increases, so does the other, or vice versa. If one decreases, so does the other. So if I wanted to state that generally, I could state that like this: x equals y. So in other words, these two variables are on opposite sides of the equation, but on the same level, essentially. Okay, in an indirect relationship or an inverse relationship, so again, that would be the same as saying this. In an inverse relationship, these two variables essentially function as opposites. So as one increases, the other decreases. So these are always going as opposites, where in a direct relationship, they're both going up or both going down. So if we wanted to summarize that generically, it's going to look like this. Those two variables are on opposite sides of the equation, but they are not on the same level. So one will be in the numerator, one would be in the denominator, or they could be on the same side of the equation. So it could look something like this. Okay, or some other number, but the point is that these two would have to be on the same side of the equation. So if this one goes up, this one has to go down to keep that number equal to the same value. Okay, so we'll be using these terms as we talk about different variables throughout section 10.2. So the first of our three gas laws named after different scientists is Boyle's law. Okay, and again, these are all named for various scientists that you can read more about in the textbook, but Boyle's law deals with just pressure and volume changing. Now, what you need to remember is that N and T, so moles and temperature, are not in the equation because they're constant. So that just means that even if we did plug these values into the equations, they're canceling out on both sides. So the only things that are in the equation are the two that are changing. And what we see is that pressure and volume are on the same side of the equation, which means if this one's going up, this one must go down. So in other words, pressure and volume are inversely related. Okay, so one's going up and one's going down. Anytime you have pressure and volume, they always work as opposites. Okay, so one thing we need to think about before we plug in here: the ones are essentially your initial conditions, the twos are essentially your final conditions. The key piece is that if pressure and volume are paired, they have to stay on the same side of the equation. The other thing we need to note is that if I have a pressure on both sides and a volume on both sides, the units need to be the same on both sides. Doesn't matter which units you use, but they do need to be the same so that they cancel out algebraically. So let's check out an example. Our second example here, so 10.2, you can read this on your own. Let's take a moment, pause the video, and read it over. All right, so our first question is, how do we even know that this would be a Boyle's law problem? Well, as we read along, it says that the gases in this tire are filled to a volume of 25 liters and a pressure just over atmospheric pressure, and we see that is 780 millimeters of mercury. So I see a volume and I see a pressure. So already that's signifying we have to use something that has those two variables. We then see that it says what is the new pressure, so another pressure, if that uninflated bag would have a volume of that. Okay, so all I see are two pressures and two volumes, which is what would ultimately direct us to our Boyle's law equation. So step one should always be to write your equation. Even if you don't know what else to do, step one should always be writing your equation. Now we're going to start plugging our numbers in. So our initial pressure was that 780 millimeters of mercury, and our initial volume, or the one that corresponded with that, was the 25 liters. We're then trying to figure out what the pressure would be if we have new conditions, so a volume of 1 liter. Now, for the record, you do not need to put units into the problem. I just do it so I make sure that they actually cancel out, but it's up to you if you don't want to do that. So, to solve this, I'm dividing both sides by 1 liter. We should all be able to do this algebra, but just in case, we would end up doing this. And what we see is that liters and liters are going to cancel, leaving us with milliliters of mercury. So mathematically, when all said and done here, we would get that P2 would be 780 times 25 divided by 1. If we pay attention to our sig figs here, 780 only has 2 significant figures, so the only way to write our answer, which is about this, the only way to write our answer to 2 significant figures is actually going to be in scientific notation. So 2.0 times 10 to the 4th, and then don't forget your unit, millimeters of mercury. So there's our basic example using Boyle's law. Now let's check out some other variables equations. So our next one here is called Charles' law. So again, named after someone. So Charles' law, instead of investigating pressure and volume, investigates volume and temperature. Once again, notice that pressure and moles or amount are not in the equation, which means that they are constant. There's one key piece of information we need to know about this equation, though. These temperatures that you see here in the bottom, they absolutely must be in Kelvin. And that's pretty much going to be a rule for the rest of Chapter 10. Our temperatures always, always, always have to be in Kelvin. And that's because in the Celsius scale, you can have negative temperatures, but that could be problematic because then you could be ending up mathematically with negative volumes. And you can't have negative volumes, right? Matter takes up space. It can't take up negative space. So just keep this in mind as we work throughout the rest of this chapter. Our temperatures must be in Kelvin all the time. If you forget how to do that, to get from Celsius to Kelvin, you take your Celsius temperature and add 273. Your book, I believe, says 273.15. I'm fine with you just using 273, but if you'd like to use the whole thing, you may. Okay? If you want to go from Kelvin back to Celsius, you just subtract 273. Now, notice that our equation here looks a little bit different than Boyle's law. Rather than them being next to each other, we see here that volume and temperature is one over the other. So this relationship must be different mathematically, and what we see here is that these are directly proportional. So pressure and volume are inversely related. Volume and temperature are directly proportional. If one goes up, so does the other. Our third law of this series looks very similar. This is Gay-Lussac's law. And what we see here in Gay-Lussac's law is that instead of volume over temperature, it's pressure over temperature. But otherwise, the equation looks very, very similar. We have one variable over the other. P1 over T1 equals P2 over T2. And again, key piece here, our temperature must be in Kelvin. Since mathematically this looks just like our other equation, that means that we have the same relationship as in Charles' law. These two variables are directly proportional. Okay? Just one quick typo here. This should say N and V are constant. But there we are. Okay? So how would you decide whether to use Boyle's law, Charles' law, or Gay-Lussac's law? It's just a matter of looking at what variables are in the problem and which ones are not. Now, what we know is that each of those laws only isolated 2 variables at a time, and that was assuming that the other 2 were held constant. However, you can have more than 2 variables changing at once. So when that happens, we want to bring in the combined gas law, which essentially is isolating each of those variables, each of those equations, but putting them all together. So notice if I ignore this part down here, we get Boyle's law, P1V1 equals P2V2. If we get rid of these 2, we have Charles' law, V1 over T1 equals V2 over T2. And then last but not least, if we get rid of volume and moles, we see that we have Gay-Lussac's law. So really, all those other formulas that we just introduced can really all be derived from the combined gas law, because if anything is constant, you can cancel it out. So let's note that if anything is constant, it can be canceled from the equation. Okay, so really, it's almost like we just need to know one equation and we can derive all the others from that. Same rules as the others. The temperatures must be in Kelvin, and otherwise everything else must match up. Same pressure units, same volume units, and then moles for both of the N values. Okay? So let's check out an example where we see our combined gas law at work. Example 10.3 says a gas occupies a volume of 7.5 liters at this pressure and this temperature. So we see so far V, P, and T. And then it says, what is its volume if that same sample of gas is at this pressure and this temperature? So again, we're seeing V, P, and T. Notice it doesn't say anything about a mole amount. It says it's the same sample of gas. So we can assume in this case that that means that N is constant. So if our mole value or our amount of gas is not changing, we do not need to keep that in the equation. So if I write my combined gas law without that, it's going to look like this. P1V1 over T1 equals P2V2 over T2. Now, once again, it's just a matter of plugging in and seeing what you can do. Keep in mind that your temperatures must be in Kelvin, and you need to make sure that all of your other units match up. So pause the video at this point, take a minute, try the problem on your own, and then when you're ready, press play to see the solution. All right, so assuming you solved this correctly and set everything up correctly, you should be getting 1.23 liters. Now note that I kept my answer to 3 significant figures because all these values that I plugged into the problem, the limiting value is 3 significant figures. One thing that you may find helpful, what I tend to do when I do gas law problems, is as soon as I see temperatures, I immediately cross them out and just write the Kelvin version underneath. I do that right as I'm reading the problem, and that just helps me remember to actually put them into Kelvin. So if you find that useful, that may be a helpful hint for you as you move forwards. If you had trouble solving this problem, keep in mind that you can just cross multiply if you really want to, and that would get you to your answer as well. Okay? So, moving on then. Our final little section here has to do with not so much a law. There's not really a formula for this, but it is sort of a relationship. So we consider that one of our experimental bases. Okay, so we have Avogadro's hypothesis. Now, we've already talked about Avogadro. We know he's important for the mole, but based on that, he was also studying gases as well. So this is the main idea, that the volume of a gas is directly proportional to the number of moles. And we can show that using this here, where this little symbol there means is proportional to. Now, that makes sense because we assume that if we have more gas, it's going to take up more space, which makes sense, right? So if the number of molecules would increase, so would the volume, and vice versa, if both would decrease. Keep in mind we're assuming here that pressure and temperature are constant, so we're only looking at N and V changing. But what I'd like to point out here with this image here are a few things. So if I have these 3 different gases, some pieces of information about these gases will be the same, others will be different. So notice one thing. Their volumes are all listed as 22.4 liters. We're going to see that that number is going to be important in a moment. We also see that they're all at the same pressure, 1 atm, and the same temperature, 0 degrees Celsius. You may recall that 1 atm and 0 degrees Celsius are considered standard conditions, right? So we call that STP, standard temperature and pressure. So we're at the same temperature and pressure. They all have the same volume, but note what is different here. They have different masses, and these numbers should look familiar to you if you look them up in the periodic table. Helium's molar mass is 4 grams per mole, nitrogen's is 28 grams per mole, and methane's is 16 grams per mole. And notice this number should also look familiar, 6.02 times 10 to the 23rd. We've seen this before. We know that that many molecules equals 1 mole of gas. So what Avogadro found as he was studying these different gases is he found that if he had 1 mole of any gas at standard conditions, they would always take up this standard volume of 22.4 liters. So that is a new conversion factor that we can now use. If you have equal volumes of gases at the same temperature and pressure, they would have the same number of molecules. But we actually know that if we're at STP, that standard volume would be 22.4 liters. So that's a new conversion factor that we can use. And we're going to apply that in example 10.4. So example 10.4, we have 2 parts here. So we're looking at this balanced reaction we see right here. Part A says, what volume of hydrogen is required to form 12 liters of ammonia? Okay, so what I know is that we're going to do some stoichiometry here because we see a balanced reaction. All right, so we'll start with part A. So we're going to start with the number in the problem, 12 liters of ammonia, which is NH3. Now, I'm going to do this the correct way so the units all work out, and then I'll show you sort of a shortcut that your book uses. Okay, so we're starting with 12 liters. Now, I want to go, remember, whenever we do stoichiometry, our goal is to always go from liters, from whatever the unit we're starting with is to moles. So how can I get from liters to moles? Well, conveniently, all of these are gases, and even though it doesn't say it explicitly, we are assuming here that we're at STP, since we were just talking about that. On a test or quiz, it would certainly be much more explicit, but we're assuming we're at STP. So if we're at STP, that means that we can use this conversion factor, that 1 mole equals 22.4 liters. So that's a way to get us from volume to moles. So we're going to plug that in down here. So 22.4 liters of NH3 per 1 mole of NH3. Now that I'm at moles, I can use my balanced reaction. So 2 moles of NH3 per 3 moles of hydrogen. So we'll plug our balanced mole ratio in there. And then last but not least, it asked us for a volume of hydrogen, hydrogen gas. So again, to get from moles to volume, I can use that 22.4 liters. Now, you'll notice if you look at this, that I have a 22.4 liter in the bottom and I have a 22.4 liter in the top. So those are going to cancel out, right? So what your book likes to do, your book likes to ignore this piece entirely and this piece entirely, and instead just set this up as a ratio saying 2 liters of ammonia per 3 liters of hydrogen. Mrs. Alvarez and myself don't necessarily like doing it that way, because then you get confused when densities start getting tossed in, thinking you can just go from liters to moles all the time, which you can't. It only works if they're gases. So I always show both of these, this one and this one, just as a reminder that what now all our units really do work, right? Liters of NH3, liters of NH3, moles of NH3, moles of NH3, moles of hydrogen, and we're left with liters of hydrogen, but the 22.4s would cancel. So mathematically, you would do 12 times 3 divided by 2 if you recognize that those 22.4s cancel out right away. So when all said and done, assuming we solve this correctly, you would get 18 liters of hydrogen gas. Okay. So you may want to write a note to yourself if you want to. If you look in your book, you'll see that they leave these out. So if you'd like, you can write something like can leave out just as a note to yourself. But again, it'll never be wrong if you include all of those. Okay, so that's part A. The final piece we'll do in this video is part B. So take a moment, jot down your answer if you haven't done that yet before I erase it. All right, and in our final example here for part B, so it says, what volume of nitrogen gas is necessary to react completely with 1.41 moles of hydrogen gas? So in this one, we're already starting with a mole value, which will make our lives a little bit easier here. So if I start with 1.41 moles of hydrogen gas, if we're already at moles, we can use our balanced equation right away. So 3 moles of hydrogen for every 1 mole of nitrogen gas. So we'll use our balanced equation to write our mole ratio. And then our final step would be, if I want to know a volume of nitrogen gas, once again, we're assuming we're at constant T and P, specifically STP. So we can again use our new conversion factor. 1 mole of gas takes up 22.4 liters at STP. So again, all of our units cancel, leaving us with liters of nitrogen. So when you do your math, paying attention to significant figures, you would get 10.5 liters of N2. So at this point, you should be able to complete homework number 1 from the textbook. These are all based on these sort of simplistic foundational laws that we will be using throughout our chapter. Keep in mind, make sure you pay attention to units, make sure you pay attention to temperatures in particular, they must be in Kelvin, and make sure you understand the difference between an indirect and direct relationship. Good luck.